with Julia, but he is back with another member of the Aeon team. And he'll be presenting on tracing the footsteps, a bird's eye view of lateral movement using Velociraptor. And joining Phalgun is Kostya Ilioukevitch, a senior DFIR consultant. Give you a quick background on Kostya. He is a senior DFIR consultant on Aeon. His primary role is to lead cyber incident response investigations, such as unauthorized access or ransomware attacks, from initial scoping to containment and eradication. In his role, he has helped many organizations in various industries respond to incidents while prioritizing business operability in the safest manner. He holds a CrowdStrike, CCFR, and GCFA certifications. So Phalgun, Kostya, take it away.
Thanks so much, Carlos. All right, welcome folks. Thank you so much for joining us at VeloCon, and we will be discussing how you can efficiently identify lateral movement and enhance DFIR investigations. So let's begin with our introduction. I am Phalgun Kulkarni, and I work at Aeon, delivering Strauss Friedberg's incident response and digital forensic services. In my role, I work on various cyber incidents such as ransomware, threat hunts, and APTs. And I love to come up with novel ideas and perform research to enhance DFIR as a whole.
Hi, everybody. My name is Kostya Ilioukevitch. I am a senior consultant here at Aeon, delivering Strauss Friedberg's DFIR services. My role, as you heard in the investigation, or rather in the beginning here, is to lead various type of cyber engagements, from business email compromises all the way to kind of large cases and matters such as ransomware incidents. And today we are here to try to enhance your investigations. And the way that we'll be doing that is presenting various forensic artifacts that demonstrate lateral movement. We then will be discussing how we took all these separate forensic artifacts and implemented them into one single Velociraptor artifact. That Velociraptor artifact returns normalized results across all these separate forensic artifacts. And lastly, how you can leverage that to create visualizations of lateral movement in a type of node graph. And kind of the beauty of Velociraptor is that it's open source and it's always easy to change VQL as you want it. And as such, as new forensic artifacts are discovered or someone would want to implement a particular artifact into the Velociraptor artifact, that will be done through continuous improvement. To start off, I don't know about you guys, but I'm quite excited to go ahead and enhance my personal investigations in DFIR. The agenda that we'll be kind of following for today is we'll start off with an overview of lateral movement. What is it? How do we identify it? And then we'll pivot over into identifying some key forensic artifacts to identify this lateral movement, covering stuff like event logs, registry keys, as well as remote access tools. Then we will present our brand new Velociraptor artifact. What is the point of it? How does it work? Why did we create it? And then lastly, we'll talk about visualizing this data using the Elk Stack and Grafana, meaning how are you able to integrate all these tools to create some sort of visualization of your data?
Thanks, Kostya. Now let's talk about lateral movement for a bit. So in DFIR engagements, one of the commonly asked questions is how many systems were affected by a threat actor in a network? And to answer such questions, investigators need to enumerate lateral movement. So let's get to know what lateral movement is. Let me tell you a story. Once upon a time, there was this beautiful unaffected network. But out of nowhere, one day a threat actor appears and decides to compromise one of the machines in the network. Now, once they gain the required credentials, they can move to any system in the network. And this movement together is known as lateral movement. So let's see how we can identify lateral movement. In DFIR investigations, we utilize forensic artifacts to extract the required information. So let's take a minute and discuss what a forensic artifact is. So basically, Windows introduces features which are aimed to improve user experience. Let's consider an example here. So on the left-hand side of your screen, we can see that a user can use jump lists to switch between multiple RDP sessions. But the same jump list, when parsed, can also be used as a forensic artifact and can get us the required information. So basically, Windows features are utilized as forensic artifacts. Now let's get to know more of such Windows forensic artifacts, which can help us identify lateral movement and that are also included in our Velociraptor artifact. And importantly, we also cover interactive as well as non-interactive lateral movement. Interactive meaning that the user input is required to access a remote system, and non-interactive means that a user input is not needed to access a remote system. So let's begin by talking about Windows event logs. Now, event logs can contain a lot of information which can be helpful in DFIR investigations. So let's begin with security event log. Now, whenever a user logs on to a system, that activity or that event is tracked in the security event log. And thus, it is one of the most commonly used artifacts to identify lateral movement. We begin by addressing event ID 4624. It suggests that a success account was logged on successfully. And this event ID can be found on the destination system. And we categorize this access as incoming access, meaning that a user accessed the destination machine from a source machine, so that the access is coming from a source machine. We represent it by a red arrow. Next, we have event ID 4648. This suggests that a user tried to access a remote system or destination system using explicit credentials. And we categorize this access as outbound access, meaning that this artifact or event ID can be found on the source system. And it is represented by a blue arrow. So basically, if you see a red arrow in the further slides, it means that the access type is incoming. And if you see a blue arrow, it will mean that the access is outgoing. And similarly, we include multiple event IDs from the security event log, which symbolizes successful logons, attempted credential validations, reconnections, and network share access as well. Next, let's talk about the system event log. In system event log, we specifically target one event ID, which is 7045. And this event ID symbolizes a service is installed on a destination system. And to be more specific, we only target PSExec service install, which can be found on the destination machine. Now, why do we include this event ID and specifically PSExec? So at times, threat actors will utilize PSExec, which is a built-in Windows utility, to either access a destination system or execute a remote command. So it can be helpful in determining how a threat actor either access the system or executed a remote command. Next, let's talk about RDP or Remote Desktop Protocol event logs. Now, RDP or Remote Desktop Protocol is one of the most commonly used methods by threat actors to move laterally in an environment. So we include event ID 131, which means that a destination system accepted a RDP connection. Next, we have event ID 1149. It suggests that a RDP authentication was successful. And we also include event ID 21, which means a successful RDP logon. Now, all these three event IDs can be categorized as incoming access, meaning that These event IDs can be found on the destination machine, and the information will also include the source IP as well as user who was associated with the activity. So let's talk about outgoing RDP access. We enumerate event IDs 1024 and 1102. Both of these event IDs suggest that a user tried to access a destination system using remote desktop protocol. And as I mentioned, we can categorize these event IDs as outgoing access. And sometimes threat actors may also utilize WinRM or Windows Remote Management. Again, this is a built-in utility which can be used to access a system remotely or execute remote commands. So we enumerate event ID 6, which means that a remote connection was established from a source to a destination system. And this event ID can be found on the source system, which will contain the information about destination system. Next, we have event ID 91, which suggests that a destination system received a remote connection from a source system. So it can be important in identifying how threat actors move laterally or access multiple systems at the same time. And lastly, for the event logs, we also include server message block logs or SMB logs. Now, SMB, again, is a built-in utility which can help computers talk to each other in a network. And threat actors can also utilize this feature to either access or execute commands. So we include event ID 3000, which means that SMB was used to access a destination system from a source system. And event ID 30806, which symbolizes that SMB connection was re-established. So we can correlate both these event IDs to determine when was the actual SMB connection established. Again, all these event IDs from various event logs can be helpful in determining lateral movement as well as remote command execution.
All right, now let's talk about some registry keys. Particularly, we'll be focusing around the anti-user.dat hives that are found in user profiles. And a lot of the keys that are found and we'll be talking about here are used to either supplement or to enrich either gaps of visibility in your logging, or essentially to correlate against your known good logs just to ensure that something did occur. So first up, we'll be talking about the terminal server client keys. Particularly, we'll start off with the server's key, which contains information about systems that were accessed leveraging the remote desktop protocol. And the information in here, or particularly the data value, would include the host name and the user associated with that remote system. Next up, we have the default keys. These keys also, likewise to the servers, contain information about remote systems accessed leveraging the remote desktop protocol. And in here, we'll see a value name MRU and most recently useless, which suggests some order of access, with MRU 0 being the latest. Next up, we have the network keys. And these in particular are kind of in and around your SMB activity. So subkeys will contain drive letters of mapped shares. And the remote path actually does include the map share name itself, which you can leverage to determine the destination system that was accessed. Then we have some more Explorer keys under current version. We have mount points 2, which includes the name of the remote share being mounted or mapped on the source system. This could be, again, leveraged to identify some type of SMB access and this would be non-interactive part of the overall artifact. And if you don't have, for example, SMB logs and you're trying to correlate a type 3 logon, you can try to reach the source system and see, okay, well, this activity would explain my other logging that I'm seeing. Then we have map network drive MRU, and the data contains map remote shares. And again, it is an MRU list, so it does suggest some order of mapping between latest to earliest. Some more keys found in here. We have the run MRU. Again, another most recently used list, but particularly revolving around the run utility built into Windows. And it does, depending on how you use it, can contain some critical information in regards to lateral movement, either through SMB or for something like RDP. There is also an MRU list, as the name suggests, so it does have some indication of ordering in terms of most recent to latest. Then we have typed paths. So this is a key. This particular key is related to typing something in your Explorer window, and it may contain information on remote shares being accessed via the Explorer window. And it does have some a quasi kind of MRU listing based off of the URL value, with URL 1 being the latest that was typed. Next up, we'll cover some shell items. Now, similarly to all of the other kind of SMB registry keys that we covered, as we may know, shell items are typically used to identify data access. But what if that data access is a remote system? So that's something that we could leverage to identify some sort of non-interactive lateral movement from a source to a destination system. So our two kind of interests here would be shellbags. So shellbags are populated when a user would interact with Explorer window, particularly on folders, and that's when they get populated, and they're found under the shellbag MRU of both the NT user and the user class.dat file, and the LNK files, which are found under the most recent of your user's app data folder. And in here, we'll see also potentially, if it does exist, remote access that contains either their host name or IP or a share name of the destination system being accessed. Now, one of my personal favorites, and this has definitely helped me out quite a bit, is user access logs. So user access logs, before we kind of dive into it, are found particularly on Windows servers 2012 and above. Why do we really care about user access logs? Well, typically, I don't know about you guys, but when I'm in a DFIR investigation and I have a really key critical server that I'm trying to identify lateral movement, I only have logs for like a week. And at that point, how do I identify whether or not a particular system was accessed by a user? Well, that's when user access logs can become quite pertinent, as the data that's recorded in them, depending on the roles of the server, can be very key to identify some sort of lateral movement and help to point you in the right direction. So in here, in this particular system32 log files, you'll find a couple MDB files. They are just the ESC database, and kind of the first one that we'll talk about is the current one. This contains information on kind of remote access based on the roles assigned to the server itself, but it'll contain information regarding the source system and the username and that type level of access that's related to the roles, and that could be leveraged to identify lateral movement when you do have a big gap in logging. Furthermore, the system identity MDB file will contain information regarding the roles themselves that are assigned to the system. So that could be leveraged to identify, okay, well, what was the purpose of the server if you don't necessarily have a good line of contact with your client? Otherwise, there are also GUID based MDB files, which would contain information and data for up to 2 years prior of the current year. So again, let's say you have a lack of logging and you have quite a big gap in your visibility. You can, if they're available, try and use the user access logs to correlate and try to identify lateral movement that you perhaps are not able to see elsewise in your security logs. And particularly when it comes to our artifact definition, we have a key few roles that we're kind of interested in particularly, and we filtered for them specifically. This would be anything regarding to a file server, remote desktop, web server, or FTP server. The most common one that you'll probably come across is a file server, as nowadays almost anything is a file server, especially when it comes to Windows servers. But regardless, that's typically what you would be expecting to see, at least in some sort of level from a UAL perspective. Next, we have remote access tools. So before we go on, what do we mean by remote access tools and why do we really care about it? Well, as we've seen kind of in the industry as a whole, is that threat actors have begun to pivot into leveraging remote access tools to ensure they maintain persistence within an environment. So this might be something like TeamViewer, might be something like Screen Connect, something like Splashtop, but It could also be other tools such as legitimate administrative SSH level tooling, such as WinSCP or PuTTY. And these tools can be leveraged by threat actors to establish, remote connections, either outgoing or incoming into a system, while also trying to blend into their environment. And this is particularly something important where a threat actor might notice that, for example, Screen Connect is deployed within an environment. As such, they would go ahead and deploy their own Screen Connect instances across the environment to ensure that they try to blend in as much as they can. So when it comes to remote access tools, there are already some pretty great artifacts available, both built into Velociraptor and on the exchange. When it comes to our Velociraptor kind of artifact itself, we incorporated the TeamViewer incoming artifact to parse the TeamViewer logging that's left over on a system. And the AnyDesk, there's two kind of competing exchange artifacts right now, the AnyDesk applications and applications AnyDesk log parser. We leverage the AnyDesk at the very current moment, but both are pretty great. Moving on to WinSCP. So this is one of those tools that are legitimately used by many administrators, and we typically do see it used by threat actors to establish SSH connections to destination systems, whether that may be to potentially try to pivot from a Windows environment into the Linux systems, or perhaps for methods of exfiltration, right? They're trying to connect to their remote system somewhere on the internet to exfiltrate data. So in the ntuser.dat file, you'll find a couple keys under WinSCP2, Martin Pericary, and software share. There you'll see a sessions key, and all of these keys really contain more or less the same data, and that would be the host name or IP of the destination system being accessed, and because it's an ntuser.dat file, you can have the user associated with it as well. The public key is also stored in the sessions information, give you information on the destination system, and the data value would also include the host name of the remote system. We have SSH host keys, contains, again, information about hostname and IP of the destination system, the user associated with the activity. Last fingerprints contains information about hostname and IP of the destination system. And as if I'm on repeat, CD cache does the same thing, contains information on hostname and or IP of the destination system being accessed. So all of these four keys can be used together in sequence to try and correlate when a particular connection was made, leverage WinSCP. For SSH access, let's say a Windows system is running OpenSSH. If you're lucky, the OpenSSH is logging into the OpenSSH operational EVTX log. Now, this log is pretty cool. It contains lots of information in terms of inbound connections. Logged as EID4, it'll contain information on either successful or failed attempts. And that could be leveraged to identify successful authentications through OpenSSH. For Atera, there is a software key that is added into your system when you do have an inbound connection, and it does contain hostname, the email associated with the instance, account ID, and agent ID, and that could be leveraged to identify when a particular connection inbound was made to a destination system. For PuTTY, you'll find pretty much the same information as WinSCP. One of them would be the SSH host keys, and that contains the host name or the IP of the remote system being accessed via SSH. For Splashtop, there is a software key that is installed under WoW 6432 node, Splashtop, remote server client info. That will contain hostname, IP, and email associated with the instance of the source machine being accessed into the destination system. There is also sometimes a event ID 1000 that's logged in your application log, which does contain hostname and email. We've also seen sporadically a Splashtop event log itself, although in our testing, we haven't really been able to concretely reproduce it to the effects that we would be able to incorporate into our artifact, but that's something that's a work in progress. For Screen Connect, there is a event ID 100 that is logged into your application log. Unfortunately, it's not very descriptive. All you really have is that a cloud account administrator connected. That could be used to leverage and figure out that some sort of remote connection was made to the system using Screen Connect, although it doesn't really give you a lot of information on what that host system was that made that connection.
All right. Thank you so much, Kostya, for walking us through all the amazing artifacts which we can use to identify lateral movement. Now, let's talk about the Velociraptor lateral movement artifact and why we decided to build it. So, Kostya, let me ask you a few questions before we move ahead. So, how do you parse multiple artifacts and analyze them?
Well, typically I would start running hunts one by one for particular type of lateral movement or exfiltration that I would want, and then I just go through them one by one.
Okay. And let me ask you, were you aware of all the artifacts which we discussed in this presentation?
No, I was not.
Okay. And lastly, let me guess. You also spend time cleaning or extracting useful information from multiple artifacts one by one.
I do. It involves a lot of copy pasting.
Yeah, isn't it efficient? Yes.
Yes.
All right. So let me tell you why we built this plugin. Sometimes investigators may not be aware of all the lateral movement artifacts and they may miss some of the artifacts. So in our artifact, all the lateral movement plugins or most of the lateral movement artifacts are included in a single artifact. So you don't have to search for multiple artifacts or worry about missing some of them. So everything is in one place for you. Next, examiners may need to spend time extracting useful information from various kinds of outputs from different artifacts. So our artifact gives out normalized results, meaning that every artifact result will have same headers or same columns, so that you don't have to extract useful information from each and every artifact. It's already done for you. And lastly, our output is in a format that can be easily integrated into your master timeline, as DFIR investigations most of the time needs to enumerate the entire lateral movement picture to identify what actually happened in the network. So isn't this pretty cool? Like all of the excruciating and hard work is already done for you. You just need to click few buttons. So let's see how this artifact actually works. Like we mentioned before, we include a plethora of Windows forensic artifact and combine those artifacts into a single lateral movement artifact, which is highly configurable, by the way, and Kostya will be talking more about it in the further slides. Next, we output normalized results, and these normalized results will contain a master sheet, meaning that all the results from all the artifacts will be included in one sheet. So you don't have to stitch multiple artifact outputs to create a timeline. It's already done for you. You also get individual results. If for some reason you only want to analyze security event log results, you can do that as well. And both of the master sheet and individual results will contain normalized columns. To highlight a few, we have event timestamp, source and destination system or IP as per the availability, and the user account which was associated with that activity. So Kostya will be talking more about it in the further slides.
So all the forensic artifacts that we have kind of talked about so far today are the ones that we incorporated into our artifact definition. This was inspired by various cyber incidents that we've covered many times using Velociraptor, and it's usually our first go-tos that we typically like to grab right away before anything starts rolling over and we have a very large gap in our visibility, 3 days into a DFIR investigation. It does also include remote access tools that we've discussed, as we've seen a lot of threat actors pivoting over into using them to maintain persistence into an environment. That doesn't mean that we've covered all of them being used. It's definitely a work in progress. And as we see more tooling being used by threat actors, they could be easily incorporated into the definition. At the end of the day, all the artifacts are in one single place, in one single definition. So instead of having to run separate hunts to cover everything, you just have to launch this one definition, and that's all that is required. And it saves you a lot of time. And in terms of what we mean by it's easily configurable, as we'll go through a couple of these slides next, we do have the ability to parse by dates. We have the ability to limit your users to, for example, a particular regex of interest that you want. By default, we disable all the system accounts, and we'll see a little bit more as we go along. But at the end of the day, with the beauty of UQL, anyone can add to their own or borrow the definition and add to it as they wish. So how did we do the whole master sheet? It's a little bit of, I guess, some VQL voodoo, and this was a really cool implementation in my opinion. So essentially, we have different sources for each and every single artifact. So for example, the security log is its own source step in the definition, user access log, remote desktop, etc. And then essentially, we only have one precondition. So that means that all the sources run kind of in a waterfall pattern. And that means that we more or less have kind of a predefined order to our notebook. So what we do is we just hijack the first notebook cell by adding in our own notebook definition. And in there, we basically have one giant chain that combines all the output sources of our plugin as they populate. We do limit each one by 50. So that's something you do have to consider. If you want to only include 50 of your security, but everything else, you can just remove it or just do a find and replace on limit 50 for nothing. And then because we're hijacking that first notebook cell, we do have to explicitly add that first definition for the notebook, that being the security log. So you will notice that in the first source, the security source, there is a notebook section defined, and that's how we implemented that master sheet. In terms of the output, so here we have an example of the output of a master sheet. We only took a screenshot of 2 entries, but we have terminal server registry as the artifact source here. And it gives you kind of this prefix of what are our normalized outputs. And we'll discuss them in a little bit as well. And then if you go, you can also see the individual output for that terminal server registry where we have all our terminal server modified keys. And in terms of the columns that you may have just seen, you'll notice that event time, going left to right, is the first column. The event time depends on what source the artifact it is. So when it comes to event logs, it's when the event was created or generated. But when it comes to registry keys, it's when the key itself was modified, and that's the time that we had decided to use in our event time column. Next, we have the description, which provides a short description to the analyst of the type of activity. And then we also have the artifact source right beside it to specify where the information originates from more concretely. Then we have the source system. So this would be a host name if it is available in the data itself, or a source IP alternatively, or both. If they're both available, and that would be great. But sometimes we don't really have that information. And likewise for the destination system, we have the destination system host name if it's available, or the IP if it is available. We would love to have both, but that's not always an option. Then we have a user account, so the user account associated with the activity. So for example, in a 4624, it's the account that logged in. On some event logs, you only get an SID. In practice, we do notice that, especially on systems that, or rather environments that don't necessarily have a proper Active Directory going, the lookup between SID to username is not very consistent. So we do leave it as an SID for now, and that's something that we would be thinking about changing later. Direction, we have incoming or outgoing, just to specify more concretely, hey, this is an incoming connection to the system, and this is an outgoing connection to the system in regards to where that data was parsed. Then we have an additional information column. So in this column, it's a little bit of a kind of a special one. It's a dictionary that just contains additional information about the specific data set that you're looking at. So such an example would be like a 4648. Typically, you have your originating and your destination usernames. So that's something that we, for example, would put into the additional information just so you have both of those username sets available. Or for example, for something like Shellbags that we had mentioned where it would demonstrate some sort of non-interactive lateral movement, we have the full path just in case you're interested in it. And here we're going to be kind of going through an example of us running the hunt. So we go ahead and we select it. You'll notice that we have a description on basically every single source that we have built into the artifact, with a couple key notes in terms of, for example, for Shellbags, you'll notice that we do say it's very expensive, and in our testing, that's typically the one source that does take the longest of time. So we do have it turned off by default. When you do start to configure it, you'll notice quite a lot of configuration abilities. Firstly, obviously the VTX path, and these get passed down either to sub artifacts that we call, such as the user access parser, or something that we implement just in our raw VQL. We do have system accounts disabled by default. We also remove anonymous logons by default, but that might not be something that you want. You know, anonymous logons can be very important to identify during an investigation. So that's something that you can just switch off right away. You'll see the user account regex that you can use to limit your data set to only a particular set of users that you would be interested in. Obviously, the date after, date before, we've seen them in plenty different artifact definitions, just to make sure that you're not collecting data for 3 years. Then we have the sum glob and some other kind of information that, again, we pass into the rest of kind of the sub artifacts that we call. You'll see a lot of switches for event IDs, just to make sure that, you know, if you wanted to, you can go ahead and remove it from your output. For example, for a 4672, you probably have the respective 4624. Do you really care about whether or not it was an administrative logon? You might. So by default, it's enabled. But if you really don't, you can just go ahead and switch it off, and it won't be reported back to you. So we do have event ID switches for pretty much almost all of the event IDs that we do include. And at the bottom there, you'll also notice that we have the disable shellbag switch, which by default disables shellbag parsing, but that's something that you can include if you so wish. So I'll go ahead and skip through here a little bit. Well, we missed it, but I was trying to show you how fast that the actual artifact could be. Essentially, because we're only parsing the event log, it's very, very quick. Well, the event log and registry. So in total, it doesn't take a lot of time in terms of running on a target system. As we kind of already know, let's say you run an EVTX under, you know, targeted your security log, just parsing 4624s. It's typically going to be very quick unless your event log is gigantic and you have it changed based off of your default settings. But it's very fast. At the top here, you'll notice that we have our master sheet right away at the top. Again, by default, we do have that limit 50 on each and every single source. So that's something just to consider and remove as you so wish. And then as we scroll down, we'll go to our individual outputs. So the first one being the security log. And again, it kind of goes down based off of the source definitions. And all right, I'll pass it back to Phalgun.
Thank you, Kostya. So now that we know how the lateral movement artifact works, let's take a look at how we can visualize the results generated by the artifact. And here we provide one example or one way via which you can visualize the results. So we begin by pushing the Velociraptor results or the results generated by our lateral movement artifact to Elastic Stack. We then connect Grafana to Elastic Stack and import the desired index from the Elastic Stack into Grafana. Now, why we import index is because when we push results from Velociraptor to ELK stack, the results will be saved in a form of an index. So that's the reason we need to import the index into Grafana. And in Grafana, we will be creating a node edge graph of the desired index. So let's see how the visualization process actually works. Like I mentioned, we begin by pushing Velociraptor results to ELK stack. We can do this by utilizing a custom-built server-side artifact. So you can go to server events and then search for custom elastic lateral movement visualization flows uploads. It's quite a mouthful. Yeah. It is based on the already existing elastic flows upload. The only difference is we tweak the results from the lateral movement artifact to cater to needs to Grafana software's node edge graph. So basically, Grafana needs data in some format for it to create a node edge graph. And that's what this server-side artifact is doing and pushing those tweaked results to Elasticstack. Next, you can go to Kibana, and in stack management, index management, you will be able to enumerate or see the index which we push from Velociraptor to Ilk-stack. Now, one thing to note about these index is these will be appended by underscore visualization. So that's how you know you can use any of the visualization index to import into Grafana and create visualizations. Next, you go to Grafana, you add a data source as Elasticsearch. You can search for Elasticsearch and it's already built in by default in Grafana. Next, you can give any appropriate name, the URL where the Elasticsearch is existing or is residing. Next, we copy the index, which we just enumerated from Kibana in stack management and index management. And importantly, you need to change the time field name from the default @timestamp to ID. And this is because we tweak the results generated by the lateral movement artifact to cater to needs of Grafana. And if everything goes well, you will see the index OK message and you can start building a visualization. So you can select between multiple data sets, but for this example, we will be selecting from the RDP event logs. Now, once you hit the dashboard console, there are 3 things to keep in mind. You need to change the metric column from count to raw data so that Grafana will be able to ingest that data. Next, you can change the time frame according to your investigation needs. And lastly, you also need to change the format of the graph to node graph. And once all that is done, you will see a beautiful node edge graph into your console. And you can also click on any of the edges or the arrows, and that will show you additional information such as the source and target system, the user account associated with the activity, as well as the description of the activity. So isn't this pretty cool? All you need to do is click few buttons and a beautiful visualization of your desired artifact will be on your console. It will save you a lot of time to manually create the CSV sheets for multiple visualization softwares and save you from some frustration. And that's how visualization works. Again, this is one process, but there are multiple processes which you can use, but we just decided to use Velociraptor, Elasticstack, and Grafana.
All right, now let's talk about the key takeaways, everything that we've already talked about here. So firstly, what did we learn? So we learned various forensic artifacts that cover stuff like event logs, registry keys. We also talked about various remote access artifacts, covering AnyDesk, Screen Connect, TeamViewer. We had showed how you can take all those separate forensic artifacts, combine them into one single Velociraptor artifact that could be made highly configurable and customizable as the end user wishes. And lastly, those results all come out normalized individually as well as in one master output for the end user, making it very easy to match it to timelines if you so wish, or it could also be pushed into visualization software, such as using Elkstack and Grafana. But there are many other options out there. And kind of the key visualization we typically always care about when it comes to seeing some sort of lateral movement is a proper node edge graph. For the future, we've talked about a couple things already that we would like to implement, stuff like the SID mapping, but as other Windows forensic artifacts are discovered, and there are plenty that are discovered every year, we would be circling back and adding them back into our artifact, as well as as we go through investigations. That's definitely something that we would like to keep updated as we move along. We'd also like to explore creating separate artifact definitions for Linux as well as macOS environments, and working on the visualization process. As we've already mentioned a couple times, it's not set in stone. A really great tool that comes to my mind right away would be using Jupyter Notebooks and D3D Graph. There's already a really great blog out there that talks about integrating Velociraptor into Jupyter Notebooks, leveraging Velociraptor API.
All right, and you can get your Velociraptor lateral movement artifact today from your nearby GitHub stores. So scan the QR code and it will take you to our GitHub repository where the YAML files exist. And if you found this talk to be insightful and if you learned something new, be sure to follow us on Twitter at StraussDFIR and keep in touch with our latest thought leadership content. We would also like to give shout out to a few people whose already existing artifacts were used as inspiration for building our Velociraptor artifact. And these are the meme sources. Lastly, I would want to mention that we used Velociraptor 0.6.9 and Windows